if I take it this way. So, dear colleagues, let us start our today's Kharkiv Quantum Seminar. Our guest today, the speaker is Dr. Saxena from University of Cambridge. He'll tell us about quantum criticality and emergent phases in spin and charge systems. And before he starts, in one slide, I would like to tell you about his biography in short. Dr. Saxena is now a principal research associate at Cavendish Laboratory in University of Cambridge and also a Bay Fellow at Jesus College. He is also a director of the Cambridge Central Asia Forum. After completing his thesis at Trinity College in Cambridge, he has been a postdoctoral fellow at University College and also in other places like at the University of Groningen and the other places you can see here. Recently, he has been chair, organizer, advisory committee member, and session chair of a number of international conferences. He also held the directorships of Center of Materials and Microsystems in Trent and also Center of High Technologies in Tashkent. Dr. Saxena's research focuses on novel forms of quantum order in metallic and insulating magnets, intercalated compounds, ferroelectric systems, and multiferroic materials. In particular, he has pioneered the study of model materials in which the magnetic and charged ordered states give way to exotic superconductivity and other forms of novel quantum order as a function of hydrostatic pressure. So, with this, I would like to give microphone to you, Dr. Saxena, please. If you would like to add something to what I said, feel free. So,
Thank you.
Do you encourage questions during your talk or afterwards?
In some sense, what if there are some things which are, let's say, unclear, or we can always stop to clarify them. But for discussion, it might be better if we can tell the whole story, because there are always twists and turns in what we're trying to say. But I'm open to whatever, colleagues. We are here in a scientific setting. Everything is allowed. So yeah. So first of all, thank you, Professor Shevchenko, for this kind introduction, and I'd like to first of all express my gratitude to be selected to speak in this very honored lineup of speakers you have. And I'm particularly warmed, as partly warmed and partly unhappy that it's online because Kharkiv is one of my favorite places in Ukraine, and that's thanks to Valentin Asarenko and Professor Yeremenko, who both hosted me several times both in Kharkiv and also in Ukraine, but as well as them hosting here. So Ukraine and Kharkiv has been part of my scientific development throughout. So much grateful to be here in these circumstances that we have to be online. But it's really great that you're continuing this series, and I hope I'll add a little tiny bit to the discussion that you have initiated here. And thank you again to Valentina for pursuing and convincing me to find a slot to speak. I tried to avoid online talks because they're not, you just don't feel the discussion and so on. So I'll try my best to present to you online. I will now try to share the slides, which I had little initial problems with, but let's see if we can all work out. I'm going to share them. Please let me know if you can see them.
Yes.
And I'm going
but
to...
not in the full screen mode yet. And now it's perfect.
Okay, and you can see me moving these things, yeah? Yeah,
yes.
They move. Excellent, good. All right, so with that, and again, apologies for starting a little late. Electronics wasn't, let's say, cooperating. So as a very generic introduction about quantum criticality and superconductivity, obviously, I can see many names here. and you are the people who created these words as we have them here. But I'll give you a little experimentalist version of the story. And of course, there are newer and younger people in the audience, I believe. So what I'd like to do is to lay out some general terms that how we think of quantum criticality as not only a phenomena, but as a guide and a roadmap, and we don't stick to it in a strong way, but it helps us to make discoveries and find new states. So, as many of you are familiar, um, that if you take an ordered state and we try to, let's say, compress it or change the lattice density, we lower its entropy, and it doesn't feel the need to remain ordered anymore in the quantum sense, and the transition temperature is decreased. And we can play this game and suppress it to hypothetically to zero. And as it approaches that critical point, as it's called, the ordered state starts to fluctuate and starts to interact if you have a metallic system with electrons in the system, and what you effectively doing is squeezing all that entropy into that corner of the phase diagram here near the critical point, which makes many of the states thermodynamically equivalent, and you cannot easily predict by standard methods what could emerge from that, and that's what guides us into the story. Another semantic point I want to make is that when we think of a conventional ordered state, as we go across a quantum critical point, we don't think that it's order and disorder. It's not. It's order and novel forms of order, and that's the kind of approach I will take in how I describe the results that we see. So one of the how say more prominent thing have been finding superconductivity in this regime, and there's still 30 years later, there's still a debate about it, and so I will show some previous results and see how it's guiding us to the current state of things. So I'll jump through again, establishing that this idea of tuning an ordered state and leading towards new quantum states, particularly superconductivity. When we started, it was only really understood in terms of heavy fermion systems and possibly high TC materials. But with a little bit of imagination, we can see it's quite general, happens across different things, including solid or liquid helium, intermetallic systems, organic systems, of course, oxide systems. But it's not limited only to magnetic systems, when we can see that happening also potentially in charge density waves, or so that's the initial title of spin and charge type of both sides of systems. And we will understand this through the results we have obtained. I'm an experimentalist, and we are at the Kharkiv seminars, the great history of low temperature institute and the work there. We come from similar tradition. I don't know if people kind of remember the history of our lab. It was effectively set up by Piotr Kapitsa and started with building of low temperature equipment, cryostats and compressed gases, and that tradition has continued to grow. So we use, of course, the traditional dilution fridges. In fact, this slide is a little bit needs to be updated. We can now have in the lab about 21 Tesla, and we can still reach 1 millikelvin. But this is, of course, a very difficult and cumbersome machine, but it's very good for doing particular kind of studies. Most of the data that I will show you comes from using adiabatic refrigerators rather, which we have built in-house completely. This is built by myself, students, and colleagues. And I think Valentina has seen it and participated in some of these things even. And you can see we have a kind of a system where we can put a pressure cell, so we can go down to about 40 millikelvin, apply about, well, depending on the pressure cell, between 30 to 300 kilobars of pressure. And we can do the electric resistivity and AC magnetization and some other measurements in these things. We use also a diamond anvil technology, which is an important part of the development. And indeed, to do the measurements, we need to have novel ways of treating our samples, which is still something that is of a rare art. So these are the tools of the trade, and I would kind of spend 1 minute on sort of this cooling method, i.e., adiabatic Dmac cooling, which I think needs to be more prevalent. Of course, you all know the principles. It's a slide for more general audience, but integrating this into cryostats is one of the areas of work with us as well. We are trying to do both the magnetocaloric and electrocaloric devices as cooling devices, but also the physics that emerges in these systems is a kind of a synergetic methodology we use. And we're trying to get these things be used in the lab, but also say at neutron sources, at synchrotron sources where we can, where often such technologies are not easily available, but they are becoming more and more prevalent through our effort. So going back to the science a little bit and reminding you of the general phase diagram we discussed, and again a very initial result that how we can take a magnetically ordered system, in this case cerium palladium to silicon, to apply pressure, and thus tuning is nail temperature down towards the critical point, which is interrupted by emergence of superconductivity. And here there are two things to note, which will feature later. First thing is that how the fluctuations of the order parameter, i.e., spin fluctuations, not spin waves, initially basically, in a sense, modify or break the Fermi liquid state in a good metal at these low temperatures, meaning that the fluctuations become the new scattering centers for the conduction electrons. And then there are details about the dimensionality, the kinds of magnetic order one might have. And so this is a field in itself of studying how the new quantum state and new quantum metallic state emerges in this area. And generally, people use the word non-Fermi liquid state. I often use this as a motivator for young researchers and PhD students to tell them, look, we don't know what it is. We say what it is not. We say it's not Fermi liquid state, non-Fermi liquid state. So if they work very hard to describe it, maybe their name can be attached to it, like Fermi's was. But the second, the fun part of doing this work is to see this very, putting all the theory and details aside, how we can prove things through experimental imagination and analysis. So we see superconductivity emerges. So we can relate that the emergence of fluctuations by looking at the power law deviating from t squared around this part of the phase diagram. And then we see superconductivity being suppressed. And we also see as the system moves away from critical fluctuations, the pairing mechanism also becomes weaker and eventually stops. So that's why you see superconductivity happening only here near the critical transition, not far away on this side or on the other side. And so this empirically kind of sets us to make the case that it's the spin fluctuations which are likely, maybe with other phenomena, responsible for creating superconductivity, which obviously is of course still in discussion precisely what and how, but it is empirically clear that critical fluctuations here are relevant mechanism and a dominant phenomena near a quantum critical point. And this is for the antiferromagnetic system. Similarly, we can look at the ferromagnet. Here, again, many things we can say, but I want you to focus on one particular, that same argument, how can critical fluctuations or be relevant? So they, of course, not only create superconductivity, but other forms of novel order, as I mentioned earlier. We could have, say, manganese silicide material. You can have skyrmions, and that's physics. That's not what I'm going to discuss here, or I'm not an expert of. But I want you to look at the uranium germanium 2, which was the ferromagnetic superconductor. And here it's the tricky analysis and fun as well. So initially we start with the same premise. We try to suppress magnetism and ferromagnetism in this case. But what we find is that unlike the previous case, antiferromagnetic case, you don't see a dome of superconductivity near the critical point. But in fact, there is no critical point. Here is a ferromagnet. It in fact goes more first order. So it's a quantum phase transition rather than a quantum critical point. However, interesting point is that a system is actually going towards quantum criticality and then escapes it. It jumps over it. There's still enough critical fluctuations to cause superconductivity. And when the first order transition happens, meaning the fluctuations die abruptly, we see also superconductivity is also suppressed with the same coincidence. And it's argued that since it's a ferromagnet to start with, it's potentially was the first clear case outside of superfluid helium to be a triplet case, and so on. So, so my game is to see how we can find more and more cases with different universality classes where we can try to link this phenomena empirically, experimentally. So theorists can have their own feast, try to understand these things. So I want to jump to entirely different kinds of a system as an example. So we show you how simple iron goes superconducting under pressure as well. And there are some very interesting coincidences here as well. So first coincidence is that this pressure at which from BCC to HCP transition takes place, and this is also around the pressure of the Earth's core. So which many geologists rather than physicists or chemists often described as a non-magnetic, because in language of geology or earth sciences, only the long-range order is called magnetism. But in our world, I think you'll agree that magnetism is much more subtle and much more richer. So we have found that the iron, in fact, across this transition has a kind of an HCP phase, strong magnetic fluctuations, and susceptibility is sort of like palladium is very high. And we then see onset of superconductivity again in this in iron. And the other key interesting thing is that we again see the power law deviance from T square or to some fractional power law as we approach the superconducting transition. And the thing that's not written here is that it's only very pure samples of iron which goes superconducting. You can't just take a piece of your key or I don't know whatever and compress it and it will become superconducting. You need to purify your samples to a very high degree to be able to absorb superconductivity. So it's anisotropic in some sense. And this is still very little studied. So we have the first evidence and discovery. There's no detailed neutron scattering studies or for the nature of magnetism or the pairing symmetry studies for nature of superconductivity, because at high pressures, techniques have not been developed well yet. And we are now finally coming to the place where these things are beginning to happen. So this is still an open area despite being looked at for a long time. Very few cases within the ferromagnets, and there are always some things which are called ferromagnetic, but which can be decisively called. And I think the most recent material where we see this is uranium tellurium 3. That's one of the options. So this is an area for investigation yet, despite the very tantalizing evidence to consider further. So I'm going to take a small sort of again a shift in our discussion, and I want to talk about the dimensionality. Again, looking very empirically, but when I say dimensionality here, I'm talking about electronic dimensionality, i.e. Fermi surface. So not only a structural thing, but structure, of course, is where things start. So original work on antiferromagnets, where you take a cubic compound like cerium indium 3 and you suppress it, and you have the same story that we just discussed. Tn goes down, superconductivity happens, it happens in a small bubble around the critical point. But what is intriguing is to see that if you make the system a little bit anisotropic, more 2D, i.e. put a layer of rhodium in the middle, and you see the TC jumps up by a decade. It becomes twice in this case. And this dimensionality still in a solid system definitely was very intriguing. It, of course, harks back to high TC superconductors and their anisotropy and why they have such high TC. Here we have although TCs may be much lower, but phenomenologically speaking, we go from a few tens of millikelvin to tens of from 120 millikelvin to about in low kelvins. So there's a decade as a change in TC by change in dimensionality. This kind of system. So this sets up to consider how we can potentially make these kind of systems more directly accessible. So in my case, I initially started with trying to intercalate graphite HOPG with magnetic species and see that we can make a two-dimensional superconductor. The idea being that you have a magnetic material which is 2D now by making it that way rather than growing it that way. And then you have the hexagonal structure, which arranges the spins in the system and then gives us two handles, i.e. the next nearest neighbor frustration will give quantum fluctuations in the system, conceptually speaking. Or if we have a material like in our case, we use ytterbium. So if we compress it, it changes the valence state and will induce magnetism. So that was our attempt. And we made this material, and we were very, very happy. As soon as we made it, we put it in the cryostat. It showed superconductivity higher than any other known graphite superconductor at the time, which was 6 Kelvin. However, the story is more interesting because if we more you studied the system, you found the ytterbium in the system was not magnetic at all. Nothing like what I had described earlier. It didn't provide any spins. It did not change any valence state. It was 2+ and just simply a structural material. So to try to clear this stuff to debate, we put calcium instead of ytterbium, which is definitely not magnetic and cannot be imaginably made magnetic. And the TC actually went up to 12 Kelvin. So in that era, this was a big result because nothing like this has been seen. But it also forced us to think in a different way. This actually took us away from this quantum criticality and magnetic superconductivity for a while and made it interesting to study this phenomena. Because if you plot all the graphite superconductors, you'll find that not all, they do not follow a standard density of state picture for TC or superconductivity itself even. Something else was going on. So this was, so we discussed this with our band structure DFT colleagues and consider the following idea that the carbon itself has a 2 eV band gap, which of course doesn't lead to any conductivity. But if you were to intercalate it, like we had done with ytterbium calcium, you find that the pi star carbon hybridizes with the intercurrent D band electrons and forms what we call an interlayer state. And if you're able to somehow occupy this state, you get superconductivity. So in this manner, so then when you intercalate, you cross the band, you form the new state, and that gets occupied and gets superconductivity. And if you again systematically plot this and do this calculation, you find that only in the materials where you see this band being occupied, you have superconductivity. But if you don't, you don't. So this is very few cases in superconductivity in general where you can actually predict where you will find superconductivity more or less correctly. In fact, all cases gonna work out. So this was a kind of a deviation from our spin charge story, but nevertheless interesting. It helped us think about more about 2D. It was a result which made it to the cover of Nature Physics in that era, the first issue, and these being our results up here. However, they still left us thinking, where is my 2D magnetic superconductor, which I set out to make? So after a lot of discussion and sessions, we settled on a different family of materials. And this is a major part of the research that's ongoing in my lab right now. And we selected on what we know as TMPX3 family, which is basically transition metal phosphorus X. X could be either iron or sulfur in our case. They're organized hexagonally similar to graphite, and they have weak van der Waals interaction. And so they're often even called magnetic graphene, although there is no carbon in the system. this is the chemical formulae of the materials that we are discussing, and you will notice that within this family, so there are 2D antiferromagnets which are hexagonal and honeycomb in structure, and they're layered materials which can be peeled, all of them. But as you as you go from iron, nickel, manganese, you see we find that there is a band gap increases as it goes up, and you can see the system, even the color can tell you that. But this turned out to be very interesting, and just for the experimentalists, so this is how we do our experiments for these materials. We use diamond anvil cells, and we can reach, in our case, neighborhood a little around 300 kilobars, 30 GPa, and we're able to do transport measurements on them, also a little bit of magnetization, but largely neutron and synchrotron measurements as well. So the initial measurements showed that if we compress FePS3, iron PS3, which is sort of an insulator, activated insulator, at low pressures, it starts to give way as we increase pressure, and resistivity starts to become more and more metallic type with this interesting low temperature behavior, which we'll come to in a second. But this resistivity here at 22 GPa looks very similar to that of high TC materials, those who are familiar with that resistivity, linear in temperature up to very high temperatures. And then to understand what's happening crystallographically, and so we can then track onto the spin and other parts of the band structure and Fermi surface in the material. So what you see is that the material actually first slides when you apply pressure to it, then it resettles, and in fact at the highest pressures, which is 18 GPa, sorry, about 90 GPa, it crosses over into rebonding between the bands and becomes more 3D like. And this can be tracked in a number of ways. So just look at the collapse of the C side of the D spacing. You can see that we have this drop in several of the materials except vanadium PS3. And what we also see is that this collapse coincides with metallicity coming into system. So just to kind of reiterate the motivation from back, so we wanted to have a 2D system, which is antiferromagnetic like high TC cuprate, but not oxide system, but another one, so we can establish a different way of achieving the similar physics. And sulfur, unlike oxygen, has been less studied. Its quantum state, quantum nature, and because it has many different ways it can bond angles and many different degrees of freedom it allows, which are less studied than oxygen. So we wanted to look at this family, and we found that it is proven to be quite exceptional in giving us nice results. So here you can see some interesting things. So if you look at FePS3 resistivity here, this is in the state when it's still the first slip, and then the next resettling, and then it crosses across into metallic behavior above 125 kilobars. And if you see the resistivity, once it crosses into metallic state, also becomes, what rather shows signs of fractional power laws. Of course, I'm tempted to say this is quantum critical, but I don't think I can say that yet, because such power laws can come from other things like disorder. Particularly if you look at the lowest temperatures, resistivity starts to go back up, and this is still an unresolved problem as to what could be this. So one of the key questions is that what is this power law, and then what is the ground state here when we reach the metallic part of this material. We tracked the magnetism in this thing in a very unique experiment using ILL, a neutron source. It's one of the first experiments there, down to helium temperatures and about 180 kilobars. So we could track the phase diagram, and here you can see how we see the propagation vector shifts. So you start with the antiferromagnet at zero pressure, then you modify the magnetism in the system, and then you find that at the highest pressure, system while becomes metallic, unlike at zero pressure where it's insulating, it becomes it retains its magnetism but in a different form. So it's now more of a short range order. So harking back to what iron looked like as we discussed in the beginning of the talk. And we can track that with neutrons. And this was a result which ILL liked very much. They put on their front page, and they showed how these interactions, in a sense, that we could measure through neutrons are causing this new phenomena. So I'll summarize that in this phase diagram. So you can see how the Tn, i.e. antiferromagnetism, with this, we could follow the wave vector, and we can follow the crystallographic structure and how it changes with we apply pressure as we go across. And then we have metal insular transition, which gives into short range magnetism. Now, here's the intriguing thing, which is the thing that we're working on right now, is that its sibling compound, FePSE3, i.e. selenium-3, was reported to be superconducting. So similar thing, insulator to metal transition, somewhat insulator to metal transition. In their case, they also measured S3, and they proposed that there is no magnetism in the system, but which we found not to be true, but there is magnetism in the system. In sulfur selenium system, we are searching now for potential superconductivity, which might emerge. So that would kind of make it like mimicking a model system similar to high TC superconductor. But this thing is still not clear. A number of challenges because in a selenium compound, selenium itself goes superconducting around those kind of pressures and temperatures. Then we showed you how iron does, and also iron selenide itself can be superconducting. So there's a lot of things to resolve. This is, but initial results are quite promising in terms of tuning and being able to do not just resistivity or simple magnetization, but to be able to track crystallographic transformation and the magnetic transformation with neutrons and synchrotron simultaneously with these properties, to be able to firm up the idea of what kind of band structure might give you these new quantum properties. However, still the calculation part is still to be in a sense established. These are the pressure ranges over which these materials sort of start to metallize, the C-axis collapse, which comes through it. And this is a thing I just put in for intriguing out. I don't do optical measurements or understand them very well, but the color change in these materials as you drive them through transition is quite striking. And so both from the point of view of understanding obviously the band, simple answer is, of course, the band structure is, closing and is getting more and more reflective. But what other kind of physics is emerging, given the background in magnetism, background in other fluctuations and short range order? How does that all add up together with this simple band structure, closure with metallicity, is something to be thought about. So I'm just encouraging those who do these kind of experiments optically or otherwise, to try to delve into it so we can combine our thinking. The other, just a general comment is that these materials, of course, are of much interest to people who do this peeling the single layer physics one for reasons of making devices, because of the chalcogenide type of family, which are very popular among engineers nowadays. TMDC is a very large applied device area. This is potentially the only family which is not air sensitive, and it can be handled more. That's why we were able to do those measurements anyway. So it forms a potential, application is high here, but also intriguingly, and this is not a very good picture, but small plot if you see here, and it's done by our colleagues in Korea, Jaegun Park's group, where they found that a single layer of iron PS3 still has the same Tn, nail temperature and antiferromagnetism. It's not affected by dimensionality. So again, a new idea. Before I talked about how dimensionality changes everything and gives you all these new things, but here in this single layer, atomically thin quantum material, you have in fact magnetism which is so resilient, which doesn't get affected by dimensionality at all. How do we understand that? I'm still an open question and topic of research. I'm going to now shift into, I think I'm a little over halfway in my time, so I'm going to rush through another thing, which is another area of research, another way of quantum area. So we went from all of these examples of how spin and charge systems, when you tune them, they give us superconductivity, they give us all kinds of phenomena. But the this emergence of superconductivity and emergence of this quantum phenomenon near a critical point, while being great as a fundamental physicist, it somehow still irritates me because we can never study criticality properly by itself, because all these things emerge and give us all these nice things to study. So some years ago, and in fact, it was the great influence in this was my 2012 visit to Kharkiv at the anniversary event of Professor Eremenko, and Valentina. I talked a lot to think about ferroelectrics, and I'll already give away that eventually we also end up in multiferroids. But right now, for ferroelectrics, as a model system, which is insulating, but you're still able to do the same stuff that we discussed before. You're able to tune an ordered state towards a quantum critical transition, but in the metallic system, conceptually speaking, what you have is that you have your fluctuations emerge, but you have the electrons in the system which then damp the fluctuations. And the physics that you're studying is of dissipative modes. But those dissipative modes then create condensates, and we see all this fun stuff that we just discussed so far. However, in a ferroelectric system, which obviously has been looked a lot theoretically in the past, you have a different scenario conceptually, meaning that when you suppress your order parameter towards a critical point, there are no electrons in the system, so the fluctuations remain undamped, and they are propagative modes. And the main sort of thing that slows them down eventually is long range interactions, not the standard the way of thinking about the quantum criticality as we've done in metallic systems. So in my case, I initially chose strontium titanate, much studied material, just because it's quite tunable, but has never really been studied down to low temperatures, below 1K. Often is used for many structural studies and conceptual things. But what could happen if you were to tune this material? And the results have been very satisfactory. This is just to prove the point that if you take STO, you change the oxygen 18. I think the names in the audience I know who know a lot more about this stuff than I do. But what we mean to say here is simply make the point that if you just change a little bit, it is affected a lot. So it orders, it's suppressed. You can drive it any which way. And so for a scientist like me, this is a very attractive material, so we can tune it easily. Obviously, there is this treatment. I'm just doing this as disclaimers. Yes, we know about all these various theory approaches to these things, but we're going to come down to experimental part. Phenomenologically, what we're talking about is that in terms of magnetic systems, we were looking at, as I said, dissipative modes, relaxation rate. This was our friend when in some free energy format. We are able to then translate this same kind of a picture towards the ferroelectrics, where we again many different things to see here, but it's the dispersion is what becomes our key way to calculate the measurables in the material. Yeah, and most of things here are quite, I'm sure, familiar with most of you. So what I'm going to jump down is that using that kind of formalism, we're able to then think about what happens in this regime and what would the properties look like. So chi inverse, which is epsilon, a dielectric constant, would look like T square, not to be confused with Fermi liquid T square resistivity. and then we have the heat capacity and thermal expansion and so on and so on. So in our case, we mostly measure chi, and as you would have seen from my previous slides, that we were experts in measuring metals and superconductors. So we had to develop a whole machinery to measure insulators, which took several years. And again, I would say Valentina has seen us do this from day one till now, where we are. So the very first results to absorb here is that we actually were able to find T squared dielectric constant down to nearly 40 millikelvin. Sorry, what am I saying? We did measurement down to 40 millikelvin, and down to about 2 Kelvin, we could see 2 to 40 Kelvin T square dielectric constant. And intriguing emergence of our 2K upturn, which shows up in this strontium titanate. And given the phenological treatment I showed you earlier, we are able to actually reproduce this numerically and find the system is T square, and we also can see this upturn. The second thing to think about to tell you is that that is not only in strontium titanate, but we see this thing also in potassium tantalate, slightly different temperature, but very similar behavior. And as an early start to thinking about what this could be, we think in terms of coupling of of the critical fluctuations to the acoustic phonons near the avoided QCP in the system. This was sort of predicted in this 1971 paper by Kaminsky et al. And there were, of course, papers before that and papers after that which treated in different ways. But here we clearly where this 2K, or rather this downturn phenomena shows up the first time. What this sets us is as for an experimentalist, to think about the material that you have strontium titanate, which is ordered, so which is in. So if you were to make a fake quantum critical picture, the strontium titanate sits inside it. Strontium titanate as a normal 1 oxygen 16 sits near the critical point, and potassium tantalate sits away from it. So this system intrinsically is quantum tuned, is what I'm trying to say. And it's quite interesting because I don't think many of our colleagues who work in applied areas who use them as bolometers and other devices are aware that there is a whole wealth of other quantum interactions happening, which both might have constructive and destructive interference with what they do. But in a bid to understand them more, we developed, again, dielectric measurement under pressure, and this is one of the few places we can actually take the coaxial cable into the pressure place. Most people measure it outside, so we get a further degree of resolution to be able to measure these small, tiny quantum effects that are happening. So we can go in this system to 22 kilobars and down to about 100 millikelvin using the adiabatic DMAC system I showed you in the very beginning. And here are these are not, of course, these are known results, others have shown them, but you can see the dramaticity of this thing, that how you apply pressure and just a tiny pressure, 2 kilobars, and you start to tune this quantum paraelectric state in the system quite heavily. And what really again helps us to imagine this quantum critical phase diagram, is that if we take that exponent, the T-square exponent, which is plotted over a fairly wide range of temperature at sort of 2 to 40 Kelvin in strontium titanate, and if you plot the same thing with potassium tantalate, because it's further away from critical point, you don't find that stable area that is there. And now here comes our best friend, the pressure. So here we are measuring the same thing under pressure. So this is so you take the same set of exponents at ambient pressure, then you start applying pressure, and you can start to see how it goes from being STO to KTO. You can actually push this material from being one to another, which is very both in a sense cool but also gives us a lot of information about the nature of couplings in this material, which is very well known. You can see the same thing in a different way. So ambient pressure, you have a wide rate area where this quantum critical fit works, and as you apply pressure, so we are taking the system away from being quantum critical as we apply pressure rather than towards it. and in other words, making STO into KTO. And if we then try to understand what happens to that upturn thing that we observed at zero pressure, we actually find that that thing grows, both in temperature and magnitude in a sense. But nevertheless, that minimum, you can collapse it back to the quantum critical point in the system, and so its relationship with the quantum critical point, yet the fact that it's being pushed away from it, is quite intriguing how that lags together, and what it might mean for its physical properties, something that we're trying to understand. That's the question we are trying to answer. So here we have a new phase diagram, and again I say we call it a phase diagram, but as you know, as professionals, only phase here is the oxygen 18 phase, which is actually ordered and suppressed. Rest are these lines and these crossovers that we're talking about. So much of this is known, but this low temperature phase, the one I mentioned, that which grows with pressure, without having a proper name for it, because we are just considering from theory what coupling could be. So we call it quantum acoustic phase. And one way to understand it is that that as strontium titanate 16 sits at zero pressure, having just gone through naturally a quantum phase transition, you have a kind of a globules of charge order in the system, which then, as you apply pressure, they grow in numbers and they start to interact, and which are moving slowly. And we are able to kind of model that a little bit to see if this accessibility makes sense. So this is kind of Gil Lonzarich, who was our big boss here for many years, still is, has kind of called self-consistent phonon theory, which is able to look at, produce this power laws and produce this upturn or downturn, as you call it, and then we can rationalize it by considering that there could be two things. One is that if you include this slowly moving microdomains or instantons, some would like to call it, we can actually reproduce the observed data. And also, we don't see, as if those who are familiar with that paper, and I won't go into detail, the Kamnitsky paper, it projects that how we would expect a T for dependence down to lowest temperature, but it is something that we don't find. So we tend to then call this coherence that develops at low temperature into order by disorder. This is one way of thinking about it. So and I mean, this is just a slide making the same point, but I'm going to jump ahead because we're running out of time to make the concluding remarks that what's our aim now is that we can reintroduce in this quantum critical soup, which we can tune quite easily with relatively small pressures, but we can go down to fairly low temperatures. Can we reintroduce few things? Can we introduce electrons into the picture? What would they do? As you all know, strontium titanate was the first oxide superconductor with very few electrons, and there's a huge theoretical body of work trying to understand the low density superconductivity. But now we can, in a sense, create it and step by step and have it different stages. And you can do that in a number of ways. You can dope it, you can ionic gate it, you can do, people have done exposed UV light. I don't know how that works, but people out there. But then also look at neighboring materials which have similar properties, like uranium telluride or iron telluride. And this is making this particular case that you have superconductivity, and you can imagine this is a slice. So if you take this conceptual idea that you have a ferroelectric transition going down, you have quantum fluctuations, and you have superconductivity in the neighborhood. It's implicitly connected, and this is real data. So that's a slice of that phase diagram, and you can see the superconductivity does peak, but is it directly critical fluctuation, or do we need more in the system to be able to understand that? Is again an area of research which is now re-emerged that of interest. This is, in a sense, what I was usually end my talk with by saying that this is border of order. It's a quantum wild west, and what might emerge here is something that we cannot fully always know. But tunability is your friend, and to that we need to continue developing our capacity to combine low temperatures or high temperatures with transport, magnetization, neutrons, and other kind of data. And this is the kind of work that we're doing now, working with electronics engineers and other people who know how to do these things better. But pressure is still artisan technique. It needs to become more regularized, so more people can try it and more students can work on it. So I'm going to sort of end there rather than read you this summary of the thing. So I'll stop there. Thank you.
Many thanks, Dr. Saxena, for the beautiful talk. And this is now open for questions.
Should I keep my slides up to answer any questions, or we can unshare it?
It depends on the audience if they need
Yeah, let's wait. Yeah.
slides more. Yeah. Let me start from the general question. Speaking about quantum technologies,
Yeah.
which unconventional superconductors are perspective from this side? For instance, we know about D-Wave Corporation
Mhm.
initially assumed that high temperature superconductors would be beneficial for building quantum computers, maybe in other quantum technologies. What's your vision for today?
Sure. I think that's a great question, and I'd like to answer it from a different angle altogether. The the three things I want to say. First is that the idea of how quantum technologies will evolve, in a sense, solely depends on how we conquer the heat or how we conquer the cooling. Yeah. So like, we had the steam engine era because we could conquer the heat. We could manage the heat. So here is another way of saying that the quantum technologies are going to not make progress unless we have better cooling technologies, which is what I tried to talk about in the beginning of the talk, that this adiabatic DMAG or electrocaloric or magnetocaloric cooling are needed to actually make quantum technologies a household item. Once we have that handle, when we can cool easily, like in a car, when you turn the key, you have thousands of degrees of fire happening in front of your face, and you don't even think about it. Cooling has to become that kind of a turnkey. We do it, people don't think about that it needs to be cooled. So that makes many kind of superconductors and many kind of states, quantum states available for quantum technologies, which we are kind of ignoring at the moment. We're focusing on few materials which are accessible. So we need to have a mindset change completely how we think about it and focus on making cooling our states more easier. Then I will go to second part of the answer is that when we think about superconductors, and of course you mentioned high TC ones and the debate regarding their pairing symmetry. Yeah. So, so unconventional superconductors, obviously, given the number of states they offer us and possibilities they offer us out where we're looking at, it simply matters how we're going to be able to access them. Is it optically, electrically, or in other ways? But there are two things there which are intertwined. So first one is the pairing mechanism, which I talked a lot about today. What kind of mechanisms can give you superconductivity? But then there's also the pairing symmetry. So and there's a combination thereof. So can we have a simple pairing symmetry, but a complex pairing mechanism, or complex pairing mechanism and simple pairing symmetry? And that allows us different operations in quantum technology. So what I really think is that we need to move into the state of hybrid superconductors in a sense, and different tuning states where we can achieve. And I think as scientists we have that mechanism. I just don't know how we translate that to our engineer friends. How do we make that accessible? But it's a question of having more conversation. So uh, I would bench on less in future, less on metallic superconductors, but more on obviously oxide, but also other sulfur and other will give us more tunability for finding more more states to entangle and or states to in a sense functionalize. So that's my long answer to your short question. Yeah. I think there's a hand up by.
Yeah, Andrei, please.
Yeah, thank you, Professor Saxena, for interesting talk. I want to ask maybe a naive question. This is because of some gap in my knowledge. You mentioned another electrical caloric cooling, as far as I remember,
Yeah.
side by side to this adiabatic demagnetization. Is it the same mechanism like depolarization of electric moments, or?
Yes. Yeah. You're absolutely right. It's conceptually the same thing. And in fact, actually, it's much better in one way and much worse in another. So,
yeah,
because
I wanted to ask more details about
yeah,
what
yeah.
are advantages
Yeah,
and
sure.
drawbacks.
So the advantage is that all you have to do is make a capacitor, as opposed to for a magnetocaloric, you need to find a paramagnetic salt, you need to find a way to crystallize or compress it, then you need to find a way to get heat in and out, then you need a magnet to do all that stuff, right? So okay, it's all doable, but it's lots of things. Here, all you need to do is create a capacitor and drive it, polarize, depolarize, and you can do it more easily since we have so much technology. But then spins carry a lot more heat. They have more entropy that you can play with. You have bigger effects as opposed to dipoles because they're ionic. They're stuck to lattice. You can get stuff, but there's not that much heat you can or entropy that you can move around uh, in in the system that we have. I mean, obviously, this is not a given. It's not fixed, but as we know, there could be systems where this can be done more easily. I understand that in polymer dielectric it may be because of the kind of modes they have, rattle modes and other things, which allow for this to happen more efficiently. I myself has another proposal. I didn't go into that's another talk I can give you, and this is again discussion with Valentina Sirenko on this that multiferroic materials, where we actually use the electric coupling to drive magnetic entropy, and I think that's where the answer lies, at least, and we have some good evidence in that area. So a material that I'm measuring, the two, maybe chemists know more, but I know too. There's terbium tantalite is a material in which basically we can drive this, so it becomes antiferromagnetic, and below antiferromagnetic, when you apply a field, you can get a dielectric out, then you can make, and it's an insulating material, so you can make a capacitor. So we're able to drive electrically the magnetic transition. And you can see in MCE, magnetocaloric effect. There's a very interesting quantum mechanics as well of rotational modes, which is still a new area to understand that how you'll have. So just think in terms of like if you have a spin that you drag through a field that you have a spin and you apply field and you track it, you get one kind of thermodynamics, and then you can apply the field and move the spin in it, you'll get some different kind of thing. So you can get many different ways of moving heat around, and you can do that electrically. Makes it more interesting. Yeah. We have
And
another.
do you have, you mentioned that the electric moments can store are less have less entropy capacity. What are the estimates, order of magnitude, or?
Yeah, so the first thing was first ever done simultaneously was in late 70s, or sorry, late 60s, both in the US and the Soviet Union, and strontium titanate itself and some doped version of it. And we were looking at low percentages of under 1%, 1% of like entropic cyclic cooling kind of a thing. But they did it at lowest temperature. So there are now many more materials in which you can get um, at medium temperature ranges, like say liquid nitrogen temperature ranges, you can get about 10-12% of cyclic cooling. And these polymer ones, which I'm less familiar with, there are claims of much higher numbers. But I don't, there's a lot of debate, and I don't understand how to say, I'm not an expert to understand what do they mean by magnetocaloric effect in those materials? But I just saw at the conferences a lot of discussion about it, so I'm slightly underinformed about that part. Yeah.
Thank you.
Professor Kardiuk, please.
Hello. So, yeah, thank you for a nice talk. I wanted to ask your opinion about increase of superconductivity. For example, in this cerium ruthenium, right? It is cerium ruthenium. It was increased superconductivity. You have shown phase diagram. Why is that?
You mean cerium palladium to silicon to
Yeah, I meant cerium indium, I think, and
sure.
it was,
I know which one you mean. Yeah. I'll show the plot in a second. Yeah. This one you mean?
yes. So it is quite increase of critical temperature, right?
Yes. Yeah. About almost a magnitude increase.
Magnitude.
So you go from sort of a millikelvin to a Kelvin. Yeah.
Yeah. And what do you think? What is the reason?
So we can think in terms of so if you buy my logic of quantum critical fluctuations are the ones which are helping to create these superconductors. So when you have a 3D systems, you have so the analogy that I gave earlier was that you have in a 2D system you have confinement and constraint, so you don't have a three motion in third direction which destabilizes and lowers the pairing energies. So in 3D. So if you are you just imagine your electron now sees the fluctuation we have created. It scatters and then eventually it's the both things dissipate and form some kind of a coherent state, i.e. superconductor in this case. So if it has 3 degrees of freedom, it wobbles in both directions and loses energy and remains, the TC gets lowered. If it's 2D, it retains its state better.
Okay. And about this intercalated graphite, right? You have shown the electronic structure, but I didn't understand your reasoning. What do you mean? Here, what do you think is responsible for the increase of superconductivity?
Okay, so actually you asking a very good question. I need to clarify. All I can tell you here is that we can get superconductivity. We cannot explain the TC. The increase of TC is not explained by this argument or by any arguments we have so far. What we are able to explain by this picture is that once you have the carbon pi star interconnect D star hybridize, they go below the Fermi surface, Fermi level, and then they get occupied, and you see conductivity and superconductivity in the material. And we can systemize it in different compounds to achieve that. But the TC itself, we have no answer for. So if you look at the list that I showed you, so we started with even electron doping side where you have a systematic, you can see that this doesn't increase. This shows neither the TC correlation nor the fact that it can be superconducting. So with our result, we've been able to achieve that we can show that which one it is superconducting and which is not, but we still can't explain the TC. There have been some attempts to force feed the mu star in the formula to get an answer by looking at certain phonon modes, but they're all sort of how to say, done by hand. There is no natural explanation of the TC in this area still.
And any superstructure here appears? Maybe here are the flat bands near the
Yes,
level.
you're absolutely right. They do. They do. And this was not the language we used back when we found this thing, but that is exactly what's happening here. Yeah. And in fact, we even argue that so what I keep calling this hybridization and it's interlasted is the flat band. And so what we argue is that if you twist this twisted bilayer graphene, you basically achieve the same thing by doing that. That is the same thing. And I don't know if the same applies to the Moray thing, which I less believe in. I'm still skeptical about that because as an experimentalist, I if you cannot know the exact angle of if your sample has a different angle every time, I mean, you cannot have the same one if you're dropping. So I think it's still a bit of chemistry than physics. We are actually working on doing our materials, the one that I showed you, PS3s, by growing them with known angles with known moire reflections from each other. Then we might know something. But yeah, I don't think people like me saying that it's such a hot field. But the flat, you're right about flat bands here. Yeah.
But how reproducible is this result? I mean, every time you have this compound intercalation, how easy is to get this 11K?
Every time. So if you want to get into the experimental side of it, so the samples can be grown in one of the two ways. So one is that you do vapor transport. So you have a two-zone furnace, you sublime and let whatever you want to do, ytterbium or calcium or lithium or whatever else, and that gets to your HOPG sample and goes in. And what you find is that it goes in only up to a point where intercalation happens. And then, so if you take the disk, you'll find that the edges are intercalated and the center is still pure carbon, mostly. And if you put that into a measurement and into a squid magnetometer or something like that, or heat capacity measurement, you can actually find range of TCs within the thing. So that means you have different, both staging as well as stoichiometries in the system. There's another way of doing it, which was in fact pioneered by French chemists, and they were doing it for a different reason. You make a eutectic melt of lithium and your intercalent, and then you basically drop your HOPG cut crystal into it, and that actually, lithium is so mobile, it takes the intercalent in, you take it out, you heat treat it, the lithium leaves the system, leaving a very well ordered system, and then you get a sharp TC every time.
Okay, thank you. Yeah.
I'll add one more thing here to you. What is really funny here is also chemistry-wise, if you look at the compound, you can never go above 2+ valence. If you try to go, say, for example, make cerium C6, you cannot make it. The system doesn't just explode, it just exfoliates. So there is some interesting chemistry there, which I don't know what that is. Yeah.
Good.
More questions? In the chat, thank you for this very interesting talk, and sorry I cannot use the microphone.
I'm reading as well.
Yes, there are more questions. Can you read it?
I'm trying to read. Okay, so was it? I'm not superconductor. Do you feel so? It is a very basic question in your talk. You mentioned the class of superconductors based on metal doped graphene, which transition temperatures are typical. These materials, can the superconductivity be achieved at normal pressure or at high pressure if necessary? Is there maybe particularly interesting system in the class of materials? Okay, so first answer is easy. That if you see the data, this is zero pressure. There is no. These are all the doped graphite materials are zero pressure ones, as opposed to other materials which I showed you, both heavy fermions and the PS3, which are pressure induced ones. The doped metal intercalated ones are zero pressure materials. Interesting thing is that although we didn't have time here, with pressure, superconductivity behaves in a very interesting way. So if you apply pressure to any of these materials, the TC increases up to a point. And up to a point means that it's different in different systems. So for instance, if you take ytterbium and you apply pressure, you reach a point where ytterbium starts to move from 2+ to 3+ and starts to become magnetic, or rather there's a valence change. And you see a drastic drop in TCU at that pressure. If you take calcium, you apply pressure and you can keep going for a while and TC keeps increasing. But then it has a structural transition. And this band structure we were just discussing a minute ago, the flat band, that gets disrupted very heavily. And we see again a drastic drop in TC. But initially, they are zero pressure ones. then to answer your other part of your question regarding the monolayer materials, which obviously there is a lot of debate on. From what I know from my knowledge, because I don't work on monolayer materials myself, is that the people have tried to decorate them, as it's called, to lay these atoms in the same configuration as we have an intercalated lattice. And there have been some claim of superconductivity, but as you know, in a monolayer, which is decorated, when you're measuring its transport properties, so it's not a trivial thing. You measure lots of other things from everywhere else. So there'll be no conclusive answer in that area, but that'll be very exciting if you can find one, which is where my answer previously went, that there's a potential to maybe twist these things or have different angles to form ones, but that's been done already. I'm looking at non-carbon versions of PS3s where we can do the similar things. I hope that answers most of that question.
Thank you for responding to the questions of Dr. Akhrimenko. And probably there's no more questions. And with this, Dr. Saxena, I would like to thank you very much on behalf of the attendees, on behalf of those who will see your talk recorded on our website. Thanks a lot.
Thank you so much. It's a pleasure. Thank you. Good to see everyone.
Yes.
Good luck. Yeah.
Yes, with this, we conclude our today's seminar. See you in 2 weeks.
Bye-bye.
Thank you. Bye-bye.